pass this to this one too. 1 over x. And what I've done, miraculously, is I have created this situation. Do you see that? I've created that. Now when I take the limit, x goes to infinity, 4 doesn't have an x in it. It's just going to be 4. 20, no x in it. It's just 20. But this right here, 1 over x, is going to be like, well, you could say it's this one, or you could just say it's this, fixed over infinity, and that's going to go to 0. So if that goes to 0, what's left? 4 over 20, which is 1 over 5. And we're done. 1/5. I'm curious if anyone remembers from college algebra, if you were given this function, that this was called a rational function, and we were asked to graph it, and you would find like the x-intercepts, you'd find the vertical asymptotes, you'd find the horizontal asymptotes. Remember this? Sound familiar? Yeah. Depending on which algebra class you were in and what your teacher stressed, the way that we found the horizontal asymptote is that we would look at the power, the degree of the numerator and denominator, and we would compare them. Now, you may not have done that, but most classes do. And the rule was that if these were the same, your answer would always be, no, this divided by this. Do y'all remember that? Yes. I did. I did. Yeah, you can look back. I did. Okay? That's only if these powers were the same. If the power down here was bigger than this one, it was 0. Y equals 0. If the power up here is bigger than the power down here, you don't have a horizontal, you have a slant and, whatever. But why is it that this works? Why is it just this number over this number? Well, if these have the same power, right? And these are the highest powers, like this. If these are the two highest powers of x, then when I come in with this, these two are just going to be those numbers, right? Like 4 and 20, because the x's are going to cancel. Everything else, since it has a lower power, when you divide through, should give you fixed over infinity on every single one of those. And all of those other ones will go to 0. But instead of telling you that in college algebra and starting talking about, going to infinity and stuff, which some college algebra classes we do. We do talk about like the idea of going to infinity. It's not totally off limits, but most books do like 3 different cases. All right, was that one okay? You liked it, didn't you? All right, let me try another one. 6x squared minus 9x plus 8 over 3x squared plus 2. Can anyone tell me the answer without even doing anything? Should be 2, right? Should be 2. But what's important right now is that we understand how we're going to get there, because I'm going to give you a problem in a minute that you can't do that way. All right? So what we're doing is we're first checking to see what happens. This is interesting, actually. Infinity squared should be infinite times 6 should still be infinite, right? But then I'm subtracting something that's infinite. Agreed? What happens when you take infinity minus infinity? It is not 0, okay? It is not 0. It's actually, you don't know, and it's really on here, okay, everyone? It's actually on this sheet as an indeterminate top left algebra or something, right? Yes? And then plus 8. Does plus 8 really matter? No. Plus 8 doesn't matter. So I'm going to try real quick to wrap my head around what's happening here. I feel pretty good that this term dominates this term because it's squared. But I can show you a lot easier that it does. Let me show you. I'm just going to focus that on just those two. If I take 6x squared minus 9x, I'm about to show you very simply that this is going to become infinite. I'm going to factor an x out of just these two. Now look at it. What does this go to? Infinity times, now what's 6 times infinity? Minus 9? Infinite. Now, what happens if you take an infinitely large number and multiply it times an infinitely large number? That's infinite, right? I've converted infinity minus infinity into infinity times infinity by factoring. And that, I hope, is convincing to you. Yes? Yeah. Okay. So this is infinity plus 8, which is just infinite. So we have infinity on top. On the bottom, this one's not so bad. Infinity squared times 3 is infinite, plus 2, still got infinity. All right, we got this bad situation. We got to do some work. So my rule of thumb from last problem was to look where? Where though? Just the bottom. Yes, the highest one, the highest power of x in the denominator. All right? That's where we go. So the highest power of x in the denominator is x squared. So I'm going to have to get rid of that and turn that into a 1. So I need to divide by x squared, right? So I come in here with, on the outside, what? 1 over x squared over 1 over x squared again. That's what I'm going to introduce. 1 over x squared, 1 over x squared, and I will pass those through. Basically, you're going to divide every term by x squared, aren't you? Every single term, numerator and denominator, is going to get divided by x squared. So we get limit, x goes to infinity. What?
8 over x squared.
6 minus
9x.
9 over x, right? Because you're dividing each of these by x squared. Plus
8 over x squared.
8 over x squared. Okay, that's my top. And my bottom? 3 plus 2 over x squared, right?
We just raised and fixed
Everything goes to 0 except the 6 and the 3, right? Now when I take the limit, that goes away, that vanishes, that vanishes, that vanishes, right? They all go to 0. And my answer is 6 over 3, which is 2. And that's why we tell people in college algebra, if they have the same degree, just look at the two numbers out front, because it's always going to be those two numbers divided.
If you gave us that question on the test.
You need to go through and show me what you're going to multiply by.
Holy crap.
Okay, what about this? Now that's just, that bothers. What the hell's wrong with this?
Android phone? Android watch?
Yeah, stupid thing. I looked at my watch, I didn't look at what time it was. How about this? X cubed plus 1 over x to the 4th plus x. So very quickly, where is this headed?
0. Well, I think it's going to be...
Well, no, I mean like the top and bottom. What's the top headed to? What's the bottom headed to? Infinity over infinity. We okay with that? Yeah. So this is infinity over infinity. So I'm going to come in here and remedy this bad situation with looking at the denominator, identifying the highest power of x down there, which is x to the 4th. And I'm going to introduce out here in front 1 over x to the 4th over 1 over x to the 4th and multiply through. Let's see what we get. So you're dividing each term by x to the 4th. So what's my top left term going to be? 1 over x. 1 over x to the 4th is the top right. Bottom left?
1 over 3? 1 over x to the 3rd?
That'll be this one. This one is 1 plus 1 over x cubed, like that. And now take your limit and let x go to 0. And yep, we get this goes away, this goes away, this goes away. Those all turn into zeros when we take the limit, and you're left with 0 over 1, which is okay. That's 0. That limit is 0. That okay? Yes.
Does that follow the rule with the larger denominator at the bottom of the answer?
That's exactly what it is. Yep. Yep.
So we can totally guess on the exam.
Yep. Pardon?
So we can totally guess on the exam.
Well, it can, yeah, yes. Bring your three-sided coin, and you should be able to knock this out. If you can bring a three-sided coin to class, you can probably answer any question. Ever. Like ever, that you'll ever need in your life.
The magic 8-ball.
Right? That's what it is. Does it seem ridiculous that there could be a three-sided coin? Oh, no.
I don't know. I mean, that's more into like physics, isn't it?
Yeah, I guess we'd have to define what a coin is before we could talk about that. But all right, let's look at this. All I did was flipped it over. See, I flipped it over. You still get infinity over infinity? Now, what am I going to come through with, top and bottom?
1 over x cubed, right?
1 over x cubed. 1 over x cubed. And when I do that, I will get top left, x, top right,
1 over x, whatever it is.
1 over x squared, bottom left, 1, bottom right.
1 over x cubed.
Okay. What goes to 0?
1 over x squared and 1 over x.
These two, right? What's still left? X over 1, which is just x, right? And where's x headed? To infinity. This is going to infinity. And this is why in a college algebra class, if the degree of the numerator is bigger than the denominator, you have these slant asymptotes that go like that or like that. It goes to infinity or possibly negative infinity. In this case, it was positive infinity.
So would factoring that be a waste of time?
Factoring that would be a waste of time. Yes, it would. And that's an important thing that you brought up because when you get to your exam, which by the way is coming up, we have 2 more sections. September 14th.
You get reviews, right? Or
That's the way to bring the three-sided coin.
We will talk about what you should look at, but I'm not going to hand you like a version of the test. You know what I'm saying? Like, your best guide is your homework.
Do you still have those files on your thing?
It should all be there, you know. All right, let's move on. I have 20 minutes. And we
oh, wait. At least it's just. So the roots just make me sad.
Conjugate. I'm glad you said that, because you should be those things should be like your neurons should be firing like that. Just because you see a root, you should just be thinking conjugate. Did anyone see a couple of months ago the MMA fight between Holly Holm and that girl Misha Tate that choked her out? Anyone see that? I don't know if you're not MMA. Who saw it? Where she jumped up on her back and choked her out? Yes? No? Anyway, golly, am I the only one who watches that? I guess so. Anyways, I thought it was really interesting because like most people in those MMA sports, when they're getting choked out, they'll like tap out, right? Well, she didn't tap out. She just got, sent unconscious. And as she was going completely out, she started punching. It's just her neurons started firing. She was just punching into the air. I thought it was interesting that the brain did
Did you
that.
think about conjugates at that point?
No, but I'm saying when you see a root, you should have like automatic neurons firing, like just like conjugate, here I come. I mean, that's the way math brains have to work. You see things and you start to think about things that could happen, could be going on, right?
No, I just kind of freak out.
And then you freak out, and then everything blacks out, and you lose the fight. But hey. Yeah, the analogy was not that you were going to be unconscious after it all. It was more just the brain works weird ways. All right, so what's happening here? The numerator going to infinity, right? 3 times infinity plus 1. So we have infinity on top. And then we have all in here, like 4 times infinity squared. That's infinite plus infinity plus 3. It's all infinite. What do you think the square root of infinity is? Still infinity.
I feel like if there's an infinity involved, it's infinity.
Not always. Like that you're going to always get infinity over infinity?
No.
Oh.
Like, say that you have an x and there's an infinity somewhere on that line, it's just going to stay infinity.
Okay.
Because you can't, once it's there, you kind of can't.
As we get more of these, that are on this chart, as we start to do more, you'll see where we have x's and we're not quite getting the infinity over infinity. We might get like the 0 to the 0. But this is all we need to worry about right now. All right, well, how is this different than the last one? The square root. If the square root wasn't there, this would be just same old stuff, right? We would divide through by, or we'd multiply top and bottom by what? 1 over x squared. If the root wasn't here, sorry. If the root wasn't here, we just do 1 over x squared, 1 over x squared, done, we're, happy. But the root causes a problem. So before I do that, I want to just remind you of something. Let's say that I have something like this. X cubed plus 4x squared. If I had that expression right there, could I factor an x squared out of these two terms?
Yeah.
Yes? And I could write this as x squared times x plus 4. That's legal?
Yes.
Okay. And because you have the square root, and that's x squared, and that's multiplication, you could really do what with this? Bring it to the outside as x, right? Yes? Yes, we could. This could come out here like an x, and this would be x plus 4. Now, I need you to agree with that, or else. Okay, well, because you have the square root of x squared. Property of roots is that you could split it into 2 roots like this. Because it's multiplication, you can split this into 2 roots like that, and the square root of x squared is x. Because these basically kill each other off. Now, technically it's absolute value of x, but we're just going to say x. As long as x is positive, which it is, so yeah. All right? Is that okay as an explanation? So the way we look at this, one way you could look at this is that if you have an x squared on the inside of a root, you can take it outside the root as an x, right? I would like for us to think about this in reverse, which you've never really had to do. If you have an x on the outside of a root, can you force it back in? Yes, but what has to happen when it goes in? It gets squared. All right? So what I'm going to try and do here is I am going to try and kill off this x squared. I am going to try and divide by x squared. I am going to do that. But I have to put an x squared in here on the bottom, but it has to start outside because remember it has to be 1, so it has to be something over itself. Whatever starts out as out here is going to have to go in and become a 1 over x squared. Right? If I go in with that, a 1 over x squared, that x squared will go away. So what can I put out here that when I push it into the root will become a 1 over x squared?
1 over
Nope.
1 over x squared.
Nope. It's going to square on its way in.
Oh, 1 over x.
1 over x. If I put 1 over x here and 1 over x, then as you pass the 1 over x through the root, as it goes in, it gets squared on its way in. And then it'll kill off that x squared. I'll do that on the next line, but let's take care of the top. What happens up top? 3 plus 1 over x. By the way, do you see we did not use the conjugate?
Could you have used it?
We can't, can anyone say why we can't do a conjugate here? You need two terms for the conjugate. I would need like the root of this plus something in order to come in with the root minus something. Yes, you have to have two terms so that when you do the like FOIL, the middles go away. There is no two terms, it's just one expression here. All right, let me go ahead and pass this into the root first. And I'm going to do this slow since this is our first time. Once that 1 over x goes in, it gets squared, becomes 1 over x squared. What happened? You all okay?
You don't need to call.
1 over x goes in the root. When it goes in, it gets squared. You square the top and the bottom, right? Square 1, square x. And I put everything that was under the radical, the radicand, I put that in parentheses because I'm going to distribute it through, which is kind of like this step here where I had the x squared. It can distribute through and go back up to this. So now pass that 1 over x squared through. What do you get? Okay, so limit x goes to infinity of 3 plus 1 over x over square root's still here, right?
Yep.
And you said it would be a 4 and then plus 1 over x and then plus 3 over x squared. And that's it. That's what we wanted. Because you see what's going to happen now? All this all goes away. All you're left with is 3 over root 4.
That'll be 3 over 2.
And that's
that'll be it.
3 halves. Are you all enjoying this? Lie to me. Come on.
As long as you understand it,
Okay. Let's make this maybe our last one. Might be second to last. 4x cubed over 2x cubed plus the square root of 9x to the 6th plus 15x to the 4th. No, don't give up.
I think now we use a conjugate, right?
You might be able to use a conjugate, but let's look at what we have first. Infinity on top, right? Infinity plus infinity, root infinity. That's all infinity. It's infinity over infinity. All right. So we got that. Got it? We have to establish that first, right? What is the limit we're looking at? And what I've been doing, the rule of thumb here was to try and cancel the highest power of x that we see in the denominator, right? What looks like the highest power of x to you? X to the 6th. The fact that it's under the square root, in your mind you should be thinking that's really closer to like an x cubed, isn't it? Okay, which it is. It is closer to an x cubed. But let's go with that. Let's go with this being the highest power. How am I going to get rid of an x to the 6th? Divide by x to the 6th?
1 over x, x6.
1 over x to the 6th. But this is inside of a root. So eventually, whatever you have out here is going to have to get in the root. And when it goes in the root, it gets squared. So what are you going to use on the outside? 1 over x cubed. Because when you square x cubed, you get x to the 6th. No, you multiply, right? 1x cubed squared is 1 squared over x cubed, come on, squared, and you multiply 6, right? So now I'll do in red here 1 over x cubed over 1 over x cubed. And be careful here because this has to go through. On the top you don't need the parentheses, but on the bottom you have two terms, don't you? So you got to go to both. What is the new numerator? 4? Good. Okay, denominator.
2 plus.
2 plus, so when you pass this through here, you get the 2, the x cubes cancel. Plus, let's see if you can do this. If you pass that through into this, it gets squared on the way in, so it becomes a 1 over x to the 6th, right? That means you're going to divide each of those by x to the 6th. Root 9 plus 15 over x squared, which now will go to 0 when I take the limit. Does anyone have a question over what I just did on that one? Because I didn't show the detail of it.
Why did you divide by x over 6?
Because when this goes in here, right, this is going to pass to this right in front, but then I'm going to force it in, and when it goes in, it becomes 1 over x to the 6th. And then that's going to go through to each of these like an x to the 6th on the bottom. Why did I do it though? Because I want the highest power of x to go away. I want it to cancel. So I wanted an x to the 6th underneath there.
And that's for every problem you want the highest power to cancel.
That's, well, it's not what I want. It's what usually works.
Right.
Yes. Yes. So that's what you want to be looking for. All right, what do we get here? 4 over 2 plus root 9, because this will vanish, which is going to be 4 fifths. 4 fifths. We have one last thing to talk about, and I can do it in 7 minutes pretty easily. You ready? What is the limit as x goes to 0 of sine x over x? Okay?
1.
That goes to 1. Everyone agree?
Yeah.
That's 1. It's not 1, right? Well, maybe it is going to be 1, but it's not. It wouldn't be because of this, right? The requirement here is that we had junk over junk. It matched in that both of these were going to 0, which they are. But if you have junk, junk, and these aren't going to 0, here they're not, they're going to infinity, then it's not, you just throw that one idea out of your head. So we need to figure out what's happening. So let's just let x go to infinity. Let's talk about what's happening. And let's start with the easier part. Where's the bottom going? Infinity. Sine of infinity, however, sine of infinity, what the hell does that mean? That means as I start to go out to the right, as I start to move to the right, what is this function doing? It's oscillating, right? So if I draw this sine function, and I start going out to the right forever, is it headed to one place? Is it headed anywhere in particular? No, it keeps on going back and forth, back and forth. It's going back and forth between -1 and 1. At any point in time, if I stop, I could be here. If I go further out, I could be up, I could be down, right? I could be anywhere between -1 and 1. So at the top of this right here, this limit on top doesn't exist. It's not headed towards a number, is it? You do not have infinity over infinity here. You don't have that. Agreed? But we can still get an answer. And this goes into on your sheet that I just handed you today with all the summary. Did everyone get one of these? Okay, I want you to look at the bottom right corner where it says fixed, positive or negative over infinity. We said that was 0, and we all agreed on that. We didn't even bother to even question it. But down on the bottom, I say here fixed means what? Non-zero or bounded. Now that's the new thing here. If the top, of course, is a number like 10 over infinity, that goes to 0. But even better, if you can just show me that the top is bounded, then it's still 0. What do we mean by bounded? If you can just show me that this is stuck between two numbers. Can you prove to me that sine's stuck between two numbers? Sine of x, no matter what x value you ever plug in, will always be between -1 and 1. Why? That's what they said in pre-cal, right? The definition of sine requires that it's between -1 and 1, right? By definition, sine is bounded. Automatically, at this point, here's what you can say. On a test, here's what you would say to me as your answer. You would say that this is bounded over infinity, and that's 0, and you'd box it up and you'd move on.
Is that the only instance that would
You could have like cosine over x, right?
So trig function x over x.
Well, tangent's not bounded.
Okay, sine or cosine x over x is bounded.
Yes. But so would sine squared plus 1 over x, right? Yeah, because what's, sine squared, if I change this, let's just change it. Sine squared x plus 1 over x. And let's change x to x to the third and make that infinity. So look at this. What's the bottom going to? Infinity. Okay, great. How about the top? This limit doesn't exist because it's oscillating, right? Plus 1, it's still oscillating. However, here's what I can tell you. Sine by itself, right, is bounded between -1 and 1. If I square that, it's now bounded between, so sine x is bounded between -1 and 1. What if I square? Think about the sine function.
Then it has to be.
If I square it, you can't have negatives, can you?
No.
So this is what sine x looks like. Sine squared x would look like something like this. It'd be a bunch of humps.
So it's not.
Because everything that was, no, it's not sine, it's sine squared. So everything that used to be negative somehow gets squared, so it can't be negative anymore, it's going to be positive. But all the places that you were 0 will still be 0, right? Because 0 squared is still 0. So you'll still have all the same x-intercepts, but all these negative pieces go up. Is that still bounded?
Yeah.
Yes. What are the two values sine squared is stuck between? 1 and 0, right? 0 and 1. Now if I add 1 to both of those, right, because that's what this says, add 1. Sine squared x plus 1 would now bound me between 2 and 1. So you're just basically adding 1 here, adding 1 there, and you're stuck between there. So sine squared x plus 1 is somewhere between 1 and 2. It's bounded. So this would be bounded over infinity, which automatically is 0. I'm out of time, but I do want to just show you something. I didn't pass around the sign-in sheet. Damn it. We took a quiz today. Did anyone not take the quiz? You didn't? What's your last name? Pardon? That's right. Okay, I will count you as Isaiah, right?
Yes.
I will count you as being here. Yeah, I'm out of time. You can start packing up. Sine functions are good for showing like things that are periodic. Almost like if you bounce a ball, it goes down, then comes back up, down, comes back up, down, comes back up. But we know eventually the ball stops doing that, right? Doom, 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 and it finally stops. If I take a function like sine x over x, if you were to graph it, here's what it would look like. I do this on the video. It would look like this. It's a sine function that starts to get narrowed down and starts to go towards 0 as you go out to infinity. Because you're dividing by a bigger and bigger number. You could even look at it this way. Do you remember a sine x? In pre-cal, a was the amplitude.
Yeah.
If I rewrite this right here as 1 over x times sine x,
So it gets smaller.
this right here is going to 0. So what's happening is your amplitude is going to 0 as x gets bigger. And so you have this thing. We call these dampened oscillators, dampened oscillations, which is more realistic in the real world. You have a spring that's moving, but eventually it finds its equilibrium point and stops. Everyone have a great week, and we do not have class Monday. It's a holiday, so I'll see you on Wednesday.